Okay everybody, this is Dr. Pennington again. I want to talk to you about one very particular reaction. It's called the Birch Reduction. And you'll see it's specific to benzene rings, alright? So from what we've seen before, so you can take benzene, which we know to be very stable, and you can hydrogenate it with a metal catalyst, but it's got to be done at a really high temperature and at a massive pressure in order for this to work. And that's simply because the benzene doesn't really want to be hydrogenated because, if you remember, it's aromatic and therefore stable, right? There is, however, another reaction you can do, and it's kind of an unusual one. This reaction is kind of similar to when we took an alkyne, this would have been something you saw last semester, and made from it a trans alkene. I don't know if you guys remember what this was. Well, what it was sodium in ammonia. This was a way to make a trans alkene. It was a radical mechanism, and this one is really very similar. It takes you from a benzene to two isolated alkenes. Okay, this is not conjugated anymore. So you know, one question might be, well, dude, why do you even bother with something like that? Well, it turns out something like this is kind of useful for a reaction that we've seen before. And even though apparently I can't write, this sort of thing is useful for a Diels-Alder reaction that we have seen before. Okay, so notice the benzene ring, all the carbons stay the way they were, but the double bonds, the three double bonds disappear again and get replaced by two double bonds that are not conjugated with each other. All right. The only other thing I wanted to talk to you guys about was what happens with particular groups on the benzene ring, because that does affect the regiochemistry of the product if we use this and this as an example. All right. So take a look at what we're seeing. In each case there is a benzene ring. All right. Here there's an R group, and if you remember, an R group means some sort of alkyl group: ethyl, methyl, propyl, butyl, tertiary butyl, whatever. This is any electron withdrawing group. Anything that can do electron withdrawing by resonance. I have a ketone here, but I could use carboxylic acid, an aldehyde, a nitrile, a ester. I could use a whole bunch of things. When we go through and do this, you'll see what happens is, if we use the same Birch conditions, what happens is, yes, we get rid of the aromaticity, we get out this non-conjugated pair of alkenes, pair of double bonds. But can you see here, in this case, we have the double bonds arranged like so, and in this case we have them arranged like so. All right. Now, the reason for that is, as I said before, this is a radical mechanism, and part of that radical mechanism involves a lone electron at this carbon here. Now, R groups, alkyl groups, are electron donating, and so that goes to destabilize the radical that will be formed here. Therefore, this carbon doesn't get reduced, and so that's why these double bonds stay like this in a product like this. Over here, these guys are electron withdrawing by resonance, which could stabilize the radical here, and that's why this does get reduced when we get the two double bonds here. Now notice, in each case, both the double bonds are opposite to each other, and they either are on the carbon with the group coming off the ring, or they're not. So you only have two options. And bear in mind, for this guy, if you drew out this, so if I have this and you drew out this rather than this, can you see that these are exactly the same thing? So it doesn't really matter how you draw it out. And obviously I can't draw this out any other way. So this is useful particularly for this product here when we come to the Diels-Alder reaction, because if I gave you that, all right, so if we had that product, let me just draw it out again down here. You guys have all seen the Diels-Alder reaction already, so you should be able to tell me. What if I was to take this crappy looking product here, take this and react it with excess diene like this, and then heat it up to give a Diels-Alder reaction. Well, what I'm hoping you guys would recognize is that all that would happen would be two Diels-Alder reactions happen. Essentially the same thing would happen twice, and I would end up with a product that actually has 3 rings in it. All right, so I'd end up with something that looks, it would look better if I could draw properly, but it's Friday, so apparently I can't. I would end up with something that looked like this, with, in each case, double bonds here and here. And this is something that you can't do from benzene. Benzene does not participate in Diels-Alder reactions before, as we've seen. This would allow you to do that. Anyway, so that's the basics behind the Birch reduction, where I can take a benzene ring and make a non-conjugated pair of dienes from it. Useful for the Diels-Alder reaction. All right, thank you.